Yeah, hello. My name is Bernhard Kroenung. I'm from the German Internet Exchange, DE-CIX, and Henning Brauer, who's a member of the team of the OpenBGPD programmers and also involved in OpenBSD developments. So what we try to do is just show you what OpenBGP is all about, how it works basically, and one of the implementations of OpenBGPD is functional route server at the DE-CIX. So first Henning will talk about the technical things, and I will try to show you a little bit what it means in practice.
Hello, I'm Henning. I started OpenBGPD 2 years ago after explanation why actually another implementation. After getting completely fed up with Zebra, which we were running before, which got us lots of bugs, bad configuration language, we've had performance problems. And since I don't speak Japanese, I had problems understanding the documentation. Zebra makes heavy use of cooperative threads, which leads to its main problem. Combined with the central event queue they lose, they can lose sessions while busy as a result of the keep alive events being way down in the queue and something else requiring all the CPU power. And, well, it just doesn't process the keep alives until the peer resets the session. Zebra's successor is Quagga, which apparently fixed many bugs, but still using the Zebra design, which I think is wrong. So, yeah, kind of unfixable. And turning a generic Unix host into a BGP speaker or BGP router requires way more than just adding a userland BGP speaking process. Designing our BGP daemon, we want 3 processes, one session engine that just manages BGP sessions, one process that we call route decision engine that actually holds all the BGP tables and takes the routing decisions or best path selection. And we have a parent process that talks to the kernel and forks the other processes. That's a nice image displaying how they work together. First time I here some time ago. You see the master talking to the kernel. The red lines indicate the functions that require root privileges. The session engine maintains TCP sessions to BGP neighbors and controls uncontrolled sessions to the BGP control utility. Once a session is established, it is responsible for sending the keep alives out and processing the keep alives from the neighbor. And it does not deal with routes at all. Update messages it receives, it just passes on to the route decision engine. And it's typically very lightweight. It's under 1 megabyte of RAM on an i386. Sometimes you see it getting bigger. It's only doing that when it has to buffer a lot of events for a slow neighbor. It runs as unprivileged user, which doesn't have any special privilege in the system, and change routes to a directory var empty, which, as the name indicates, is empty except for a logging socket. The route decision engine maintains the routing information base, means prefix table, AS path table, and assorted information. The BGP filters run there. It calculates the best path per prefix, does the best path selection, and it generates the update messages as needed. The RIP itself is split into many, many tables. They're heavily cross-linked. The goal was to avoid table walks, and in fact, we almost never need table walks. We need table walks when we have a new peer coming up, of course, sending him the entire table. And we have table walks when the BGP control utility requests the entire table to show it. Well, there's no way around that, obviously. Otherwise, there's no table walks. It's very memory efficient. These numbers are from before we had soft reconfig, but it didn't get that much worse. And you can still turn soft reconfig off. So with that, one full view needs around 20 megabytes of RAM on i386 again. And 2 full views just need 25 megabytes of RAM. This is not even half of what you need with other implementations on other hardware routers. It's very fast. It takes about 10 seconds to load a full view on a 1 gigahertz P3, and less than 5 seconds to dump the full view to your peer. And just as the session engine, it runs as unprivileged user and changes to var empty as well. The decision process. Most of you probably know that we have 2 extensions. First, check if the prefix is reachable at all. Second, check the local preference, bigger is better. Third, check AS path length, shorter is better. Fourth, check origin. 5, multi-exit discriminator, which is only comparable between the same neighboring AS, but we have a knob to always compare it if you need that. 6, eBGP is cooler, and then it's one of our extensions, wait, which is used to force traffic to your preferred uplink, may it cheaper or faster or whatever. Well, I go on to that on the next slide. 8 is a route H, which you can evaluate, and this is disabled by default. This means that older routes get preference, and older routes are necessarily the more stable ones. And the last 2 ones are only there to make sure that there's always a winner, and that's the slowest BGP ID and last lowest peer address. The wait can help a lot. More and more often you see equally long AS paths from your uplinks because they're all at the same exchange points. And for traffic engineering, you of course want the possibility to express a preference. And yeah, that's not local pref, because local pref comes before the AS path length check. And so we added wait. We know that it somewhat clashes with the wait that other implementers use. We unfortunately couldn't get up the better keyword, and we were asking people to tell us a better keyword, and nobody came up with anything, so that's what it is now. Looking at the parent process. The parent process is responsible for getting the routes into the kernel. It does the next step validation. It maintains its own copy of the kernel routing table. For that, it has to fetch the kernel routing table and the interface list at startup, and listens at the routing socket where all changes to the kernel routing table show up as messages to keep the internal view in sync. And that means, or the way we coded it, this means that if you fiddle with the routing table manually, we do notice that and cope with that instead of overwriting your manual changes. And we also have an internal list of interfaces and their status, and that is kept in sync with the kernel as well. We do know about the interface link status. It's often said to be almost impossible in Unix to get a link state. Actually, it's not that hard. And we use that for next step verification. An interface which doesn't have a cable plugged in apparently doesn't lead to usable next step. And actually, yes, that means we notice when you pull the cable and quickly invalidate the next step. We do not need periodic next stop table walks at all, like a big vendor and Zebra do, which means that we react much faster to interface state changes. There is an up to 30-second delay in Cisco routers and Zebra installations. The internal view of the kernel routing table can be coupled and decoupled from the kernel. This originally was a debugging feature because we had a problem with one of my test machines where we didn't have enough memory, but it turned out to be very useful. It's really damn fast. With a full table, it takes less than 3 seconds on a P3 750. And the parent process totally needs about 6 to 7 megabytes in full view configurations. TCP MD5 signatures. TCP sessions are not really authenticated, as we all know, so we implemented TCP MD5 signatures as security association within the IPSec framework because they are really just a special form of IPSec authenticated header. That means that I had to code a PF key interface in BGPD, which was really not fun, to interact with the IPSec framework. TCP MD5 signatures are not a new attack vector. There's people spreading that. It's pretty much flat because by the time you hit the TCP MD5 code, you already have to hit the sequence number, the port numbers, the right addresses. The chances to hit that are really low, and even then, MD5 is really, really, really cheap. So the conclusion from that is, it's kind of weak, but it's extremely easy to configure, and it works with almost anything out there, so go ahead and use it. IPSec. Since we have the PF key interface already, it was not too hard to do real IPSec, and with that, BGPD loads the security associations in the kernel, which is kind of the keys, and it sets up the flows, which kind of is the routes for IPSec. Juniper can do static keyed IPSec as well, and we are compatible with that. As far as I know, Cisco cannot. There might be some extra feature set that you can pay extra for, I just don't know. And instead of doing static keying, we also can use ISA-KMPD to do the keying for us, which also means that the keys are changed on a regular basis. With that, BGPD asks the kernel for an unused pair of SPIs, which are some kind of identifiers, and uses them. And BGPD loads the flows into the kernel. It's usually done by ISA-KMPD, but in this case, we let BGPD do it because it already knows the endpoints naturally. That means that ISA-KMPD only needs to handle the keying. And that means that ISA-KMPD needs almost no configuration. And all of those who ever had to write an ISA-KMPD config file will value that. Here's the complete how-to. Copy the key files, which are generated on the first boot on an OpenBSD box, over to your peer. Run ISA-KMPD-KA, and you're done. Integration with our packet filter. The BGP protocol is an efficient way to distribute lists of network prefixes. It's not necessarily routes. So we integrated BGPD with our packet filter. And the BGP daemon can add prefixes it learned from its neighbors into a PF table. The prefixes to add to a table are selected using the filter language, and the tables in PF use a radix tree, which is the same code used by the kernel routing tables. And that is very fast, even with a lot of entries. In turn, PF tables can be used pretty much for everything. You can do packet filtering based on that. You can redirect packets, for example, to our userline spam daemon or spam fighting daemon, which in turn means that you're using BGP distributed spam blacklists instead of using the stupid DNS-based approach. Or, that's really neat, you can do quality of service processing. There's also route labels. BGPD can attach labels to routes using the filter language. Labels are basically just 32 bytes of free text information that can be attached to the route and are stored with the route in the kernel routing table. And, well, they're not stored directly, but who cares for that implementation detail? There's a sample output where you see a route that has a label set, the label foo. Of course, then PF can filter based on those labels, which means you can write rules like pass in on some interface from route with the label foo, keep state. But it's much more interesting to use PF to classify traffic for quality of service processing or anything or stuff like that. So in this example, you pick all routes being tagged with the label MCI and put them to a queue called really slow. Your help desk can finally tell your customers that you always told them MCI is slow and you don't need to mention that you play part in that. Combining BGP information with PF capabilities is really very powerful. You can limit states per source address depending on the source AS. So you have your broadband ISPs where you know that most attackers are sitting and limit the connections to 10 per IP address or something like that. And you can also use the maximum source connection rate features in PF that help fighting DDoSes, and finally you can do that based on the origin AS numbers. Integration with CARP. CARP is the Common Address Redundancy Protocol, which allows to share an IP address in a master backup scenario. It's much like VROP, but unencumbered from patent stuff, and it's actually better because it's properly authenticated and it's faster. A typical case is exchange points, where you have one IP in the exchange point network, and yeah, what about using toolboxes there, having the IP address shared using CARP? That works without special support from BGPD, but yeah, we can do better. If we make BGPD aware of the CARP master and backup state, we can force sessions that depend on this CARP interface. We force them in state idle so they don't even try to connect as long as we are not master. The very same moment we become master, the CARP interface, yeah, we get notified about that, and all sessions depending on the CARP interface immediately try to connect to the neighbor, which in turn leads to a way faster failover. DE-CIX support, yeah, it's there now. IPv6 transport actually has been there for quite some time. I hacked it at a conference in Canada when I got bored in the talk. The IPv6 RIP is there since mid last year. And, well, there's not much to say about that because almost everything just works like it does for v4. Lots of testing needed, but so far it doesn't look bad. Let's skip over the configuration. The config file is split into 5 sections. We have macro definitions, just like in PF, no surprise, same code. We have global settings, networks to announce, neighbor definitions, and filters. This is an example where you see some macros defined on the top. Then you have the global configuration. The only mandatory global configuration is your own AS number. Router ID, it figures out on its own. The listen address figures out on its own. Hold times, there's sensible defaults. And FIP update, yes or no, means whether it starts with the kernel routing table coupled or not. And finally, there's the networks you want to announce. Neighbor definition, neighbor IP address, and in curly braces, you have the remote AS description and stuff like that. You already see TCP MD5 configured here. It's really very easy. And the last setting, you see the announce keyword, which can save a lot of work. Has 4 options. It's none, don't announce anything. Self, announce only your own networks. All, denounce everything. Or default route, just announce the default route and nothing else. On many other implementations, you need filters for that. Here's just one configuration setting. Neighbors can be grouped. Members of a group just inherit the settings from the group. There's templates. If the neighbor address contains a net mask, we just accept a connection from every host that matches that prefix net mask specification. And we inherit the remote AS number from the open message then, and clone this neighbor definition. When the session drops, we keep it cloned for a while and remove it later, so we can still do flap suppression. This is nice for redistributing bogons or blacklists or something like that, so you just define your whole router network and don't need to configure all the routers individually. Here's an example for IPSec with static keying. The long keys are a bit unhandy, of course, which directly leads to the next slide, showing the same using IKE, getting us dynamic keying, and showing how simple IPSec configuration really is with OpenBGPD. You just put IPSec ESP IKE or IPSec HA, authenticated header IKE, and you're done. Just have to start SOKMPD with it. Filter language, that's where most development work goes to currently to further improve it. It's a bit modeled after PF. Should be reasonably easy to follow. Shown here is the filters we have in our default configuration we ship with OpenBGPD. The filter language is last match, so last rule matches. A rule has 3 parts: action, which is allow, deny, or match. Match doesn't change the allow or deny state. The match part, where you can match based on prefix, prefix length, or parts, or the entire AS path. And set, where you can add prefence, modify the local preference, the metric, assign a PF table, label, etc. There's the BGP control client program, which connects to BGP using a Unix domain socket, which can query runtime information, calls a configuration reload, couple and decouple the kernel routing table, and take specific sessions up, down. Here's an example from one of my production routers showing overview. For many of you, this should look familiar. Here's a view at the kernel routing table for only connected and static routes. Here's a view to a specific neighbor. Should look familiar too. You can actually look at the timers as well. Might help in debugging. Here's a view to the next stops. We actually list the interface we see the next stop depending on if there is any, and its state, and link state and speed as far as we get that information. Causing a configuration reload or coupling, decoupling the FIPS, very easy, shown here. And well, you can take neighbors up by their name or their IP address. And the last one is special. The feedback that there's no such neighbor by name is a pretty new feature that used to not bring any feedback. So, looking glass. BGPD has a second restricted console socket now, I quoted that 2 weeks ago, which only allows for certain messages, namely those behind the BGP control show operations. Running an HTTPD in a change root environment, which is default on OpenBSD, a CGI can just call a BGP control binary placed inside the change root, giving the path to this restricted socket. And then you just need a CGI calling that, and your looking glass is done. The CGI, yeah, somebody needs to sit down and hack that, but it should be easy. And it should be ready soon. So, status quo. BGPD itself is very stable. It has to, because otherwise my company is offline. It is in use at quite some sites already, including setups with many peers. I don't have hard numbers about the numbers of sites using OpenBGPD. After all, this is free software, so nobody has to tell me that he's using it. On the other hand, quite some operators do mail me, and they usually express that they're very happy with the performance, reliability, and ease of use. And yeah, I like getting those emails, so if you're using OpenBGPD, please mail me. Some boring statistics. BGPD is 20,000 and something lines of code right now. BGP control is 2,000, and the man pages are 2,340. And yeah, they're in English. Availability. OpenBGPD has been part of OpenBSD since the 3.5 release, which was released in May 2004. There's a new release every 6 months. And there's really thorough testing. Quality is more important to us than anything else. So there's no security without quality, and for us, quality also means correct, up-to-date, and English documentation. And now I pass on to Bernhard to talk about OpenBGPD at the DE-CIX.
Okay. Some short words about the DE-CIX. DE-CIX is one of the biggest European exchanges. Actually, it's the biggest in Central Europe. We have about 170 connected ISPs. We have 264 ports connected. So there's a lot of BGP sessions you have to handle if you want to peer with all. Current traffic is roughly 55 gigabits on the public LAN. We expect about 30, 40 additional gigabits on private interconnects where you have no control over. Of these connected ISPs, about 130 using the route server. With 155 sessions, so it's not only one-to-one, it's also ISPs connected that have more than one connection to the route server. At the moment, the route server itself handles 16K routes. We have our current setup are 2 Quagga-based route servers and an additional for external routing. Currently, the route server gives the newly connected ISP or member some advantages for setting up very fast the connection to the internet exchange. It's just one connection and you get approximately 130 peers, so that's approximately 75% of all connected ISPs. We have a transparent AS setup, also a normal non-transparent setup with the AS number 6695. So you can choose if you want to have one AS path longer or you don't want to see the DE-CIX AS path when you connect to the route server. It's an easy setup. We kind of label routes depending on which switch location the ISP is connected, so that you can also choose how you build your redundancy, how you configure your setup if you have one or more port connected to the DE-CIX. And we can control, or the peer can control an announcement or non-announcement to some peers very easy with communities as usual. The problem as usual with route servers is that you might not see the complete route table because some AS paths are not visible because of the best selection algorithms. You have to set up your own peers if you like to avoid this. Otherwise, we have to do it with the software, so that's one project goal, to have some kind of per peer view of the routing table depending on the peers you want to see or you want to peer with. Yeah. Why OpenBGPD? We had some experience with Quagga. Quagga is quite okay, but not that stable. We want to implement also MD5, which is not probably integrated in Quagga as I know yet. There are some patches around, but not stable ones. Also, we want maybe have the chance to use IPSec if you have a hardware that supports that. What we do with cooperation to the developers is to have some close contact to improve the filtering compatibilities, to have some chances to improve what we use at the route server, and as I told you, the best path selection process. The other thing is if one process dies or one machine dies, that we have a redundant setup, maybe in the future also a hitless failover so that the TCP states are synchronized. At the moment we have a test server running. We add some peers there to test everything, and if this works up for the people okay, then we maybe exchange the Quagga soon at the DE-CIX. Configuration is very easy. You have, as I told you, communities. You can say, okay, we don't want to have any announcements to any peers. We want to have announcement to selected peers. We don't want to have an announcement to selected peers, and also don't announce anything. Things like adding a PSAS is based on communities. It's very easy. Okay, just to the end, some thanks.
Yeah, I'll skim over that because we're out of time. I just have to thank Claudia, who's writing OpenBGPD with me. There's more people involved, but we are the main ones. There's Andrew paying most of Claudia's work, Theo, who finally kicked my ass doing that. Wim for continued support, and of course DE-CIX for funding this trip and the great cooperation. One unavoidable last page. This is all free software, but of course there's funding needed, so if you can and use it, please donate or at least buy our CDs. And yeah, if you want to hear more, I'll speak again at the Toolsbooth later today at 4 p.m. in the Parisian room. Yeah. That's it. Thanks.
Okay. Thanks to you at the Peering Booth or the Toolsbooth.
Thanks, guys. Looks like we have some mics.
Randy Bush, IJ. Your route server, you said you allow label tagging to allow people to handle redundancy, et cetera, et cetera. That has an implication that your labels are transmitted through BGP. I'm a little confused.
No. In BGPD, you can label routes, and the label is stored with the route in the kernel routing table, but it's not redistributed into BGP again.
Then if I talk to your route server and routes are labeled and you say I can make decisions based on them, how do I get them?
No, it's just community thing. So like we label a community if it's from switch number 1 and another community if it's from switch number 2 and 3, etc. That's the only thing we do.
Yeah, labels is not communities. Yeah, that's different things.
Hi, Brenda with River Domain. But unrelated question: Do you know if CARP can be ported to other distributions?
Pardon?
CARP
Yes.
can be ported to other distributions.
There is a userland implementation that works on almost every Unix systems, but of course userland is the wrong place to solve it. I'm not certain about the state of it in FreeBSD. It might be there. I'm not certain. Same for NetBSD. There definitely is code, but I'm not sure whether they finally imported that.
Because correct me if I'm wrong. It initially started. It was designed for OpenBSD, right?
Yeah.
Okay.
It also
Thanks.
run on Linux.
No. What?
OpenBGPD.
No, it does not run on Linux.
Not fully, but okay.
It does not run on Linux.
Yeah. Back microphone.
Sandy Murphy at Sparta. I was curious about your description of using an IPSec SA to do the TCP MD5 stuff. You mentioned that this isn't an attack because the TCP processing of sequence number and stuff occurs before you do the checking.
Yep.
But I'm wondering how you prevent the IPSec kernel stuff from occurring before the TCP gets a hold of the packet. So, if you're using an IPSec SA.
Okay, if you're using encryption, IPSec ESP, of course you cannot. If you're using TCP MD5, the packets itself are not encrypted. There's just an authentication checksum, right? There's the MD5 signature, but you still have all the TCP information in clear text, so it's easy to check them before you actually bother checking the signature.
Okay, so if you're using an IPSec AH, is that what you mean?
No, this is for TCP MD5.
Okay, but you said you were using an IPSec SA for the TCP
Yes.
MD5. Okay, so maybe I need to talk to you later.
Well, we just implemented in the IPSec framework to have the same interfaces to userland because, if you think about it, it's just a special case of IPSec AH.
Okay.
And even for IPSec, the TCP packets are checked. Well, it's not TCP then, but there's checked what you can before.
Secondly, you said something about picking 2 SPIs, and IPSec SPIs are usually picked by the destination. So do you mean that one side of the peering session picks the SPI for both sides of the conversation?
They don't need to match.
They
You
don't
just need 2. You need one per direction, but they don't need to match on both hosts.
Okay. And your discussion about cloning sessions, accepting connections from anything on a network, how does that work with TCP MD5? Do they have to have the same shared secret on all of those network hosts?
Yeah. If you want to use TCP MD5 and different passwords, sorry, you have to configure that for each peer. No way around that.
Okay. Do you have any mechanism that would prevent people from allowing that cloning stuff without doing TCP MD5?
There's really no reason to prevent that. It depends on what you use it for. If you set up a server that redistributes a bogon list, there's nothing wrong with everybody connecting to it. So you could place neighbor 0.0.0/0. That's fine. So I don't see a point in preventing anything like that.
Preventing BGP connections from anybody in the world?
Why not? If you're just redistributing and if you're not accepting anything and just redistributing a bogon list, why not?
Okay. All right.
It's just an option, so you have to know what you're doing. So it's not enabled by default.
Of course not, no.
Okay, I think we need to move on.